my name is Jadin Moorman, and in this video we'll be explaining the density of a log floating in water. So, my marker's weird. This is assuming first off that the log itself is a cylinder, and second off that we know the radius of the log. So to start off, we'll have a quick drawing of the log. There's some water here, which is floating. Is floating in this water. So this log has a height from the surface of the water to the top of the log, the radius r that we know, and then a length L. And so first off, the first thing we're going to start off with is the idea that essentially the buoyancy, the buoyant force, is going to be equal to the weight. So we're essentially able to say here that m, the mass of the water times gravity, is equal to the mass of the log, ml, times gravity. Obviously here we can cancel out the g's, and then we can move on to saying that, so here we can say that the gamma, or density, of the water times the area that is submerged, so the area that is below the surface of the water, times the length of the log here is going to be equal to the density of the log, so gamma L, times the area that is above the water line, so, or the, H, and that is also going to be times length. So we cancel out the length, and we get this nice equation. Okay, we're restarting, but it's going to be a good one. I promise. Just don't. Hi, my name is Jadin Moorman, and in this video I'll be explaining the density of a log floating on water, or how to find the density of a log floating in water. So first off, I just have a basic drawing, which shows that A, we are assuming that it's a perfect cylinder, and B, that we know this radius. So this log has a height h of the area that is floating above the water, a radius r of the cylinder itself, and the length L of the log. So to start off with our derivation, we're going to start off with the idea that the buoyancy, the buoyant force, is going to be equal to the weight. So the mass of the water times gravity is equal to the mass of the log times gravity. And obviously here we can cancel out gravities, and then we can do some substitutions. So we have gamma, or the density of water, times the area of the submerged section. So we have a section that looks like this. We have a section that looks a bit like this that is above the water, and a section that's going to look a bit more like this that is below the water. And so we're going to be working with that for pretty much the entirety of this video. So we have this section which is above and this section which is below. So we have the density of the water times this area times the length is equal to the mass of the log, not the mass, is equal to the density of the log, so gamma L, pi r squared times the length. And so yet again here we are able to do some cancellations. We can cancel out the lengths, which leaves us with this nice equation. So to start off, so in order to move on, we need to kind of make some postulations. So first off, we have this concept of these two areas. So we have the whole area, this, which is the cross-sectional area of the log. So I'm going to say that this minus the surface, the area, the cross-sectional area of the part that is above the water is equal to the cross-sectional area of the one that's below the water, because obviously you can say that the reverse is true. The whole is equal to these two parts added together. And so we're going to be able to use this very basic, obviously, concept or equation, so that essentially the area of the log is equal to the area floating, or area of the log minus the area floating is equal to the submerged area. And so we can flip this around, obviously. We can say that the area of the log is equal to the submerged area plus the floating area, or we can say that the area of the log minus the submerged area equals the floating area. Moving on a little bit, we're going to draw the cross-sectional area of this log. So we have this, and this allows us to look at it a bit more in depth. So in order to find the area of this, we can say that a circle has a sector, which is just the center point where the radius is measured from, and then two straight lines that go out. And so this is essentially the top part of a sector, where the line is where the water level is. And so we can say that this area here subtracted by the area of this cone is equal to just the top area. And so essentially this allows us to use the idea of finding this, we find this triangle, and that will actually give us the area of the top part. And so in order to start finding the area of the triangle, we're going to separate it into two right triangles. And then we're going to be able to say that this is the radius and this is the radius. And then this right here is just the radius minus the height above water. And then this is some unknown x, where we don't really have a way to find out the length of the section that is above water. So, to move on, we're going to be able to figure out, so the first thing we want to do is we want to find the area of this sector. So this, I'm going to use, this sector. So this region between this line and this line, which has an angle down there. The way you find the area of a sector is you take the area of the whole circle and then you multiply it by some fraction, degrees or radians. So if we're going to use degrees here, there are 360 degrees in a circle. So then we divide 360 degrees in a circle. We divide this by, so we have this angle and this angle, which are equal to each other. And so if we call that angle theta, then the area of this whole sector, or the angle of this whole sector, is going to be 2 theta. So whatever theta equals will give us, so 2 theta over 360 gives us the area of the sector. And then we want to find the whole area, which is going to give us pi r squared. So actually, I realized that using radians as a way of measurement is going to be a lot better here. And because, as you can see here, the amount of radians in a circle is 2 pi. We can cancel out these pi's, and we can also cancel out those 2's. So that's my bad, but it was a pretty simple mistake. So we can cancel out these pi's and cancel out these 2's, so essentially I'm going to drag this up here. We are saying that the cross-section, or the area of the sector of the cross-section of the log is theta times r squared. And we need to find something, or a substitute for theta, because we are not given the angle of the sector, which is pretty easy to do. We just take the arc cosine, I believe, because the adjacent is a known and the hypotenuse is a known, because the adjacent is r minus h and the hypotenuse is r. So arc cosine is going to be, so cosine is opposite over hypotenuse, so it's going to be hypotenuse, which in this case is r, over r. No, that's the inverse, because arc cosine of r minus h over r, because cosine is adjacent over hypotenuse, so it's r minus h all over r. So you have that in parentheses. And so that equals theta. And so in this scenario, we can actually replace this arc cosine r minus h over r of the radius minus the height of the radius times r squared times that quantity equals the area of this entire cross section. So we have, in our 3 steps here, we know this now. We have figured out the area of the entire section. And so the only thing we have left to do, so this equals the area of this bad boy, okay, of this sector. And so then, in order to be able to find the total area that is above water, we just need to find the area of this triangle, which shouldn't be too hard. So area of a triangle is just going to be base 1/2, the base, which in this scenario is going to be x, an unknown quantity, times the height, r minus h. So as I said earlier in this video, we don't know what x is. X is just a placeholder for us. And so we're going to be able to use the Pythagorean theorem, a squared minus b squared, right? A squared plus b squared equals c squared. And this will allow us to find x in terms of r and h. So essentially, we are saying that c, or in this case, we can replace that with x, is going to be equal to a squared plus b squared, or the square root of a squared plus b squared. A squared in this scenario is going to be r squared, plus the quantity of this is wrong. So a squared plus b squared, where a and b are legs and c is the hypotenuse. So what we're actually looking for is one of the legs. So a squared in this scenario will become x squared equals c squared minus b squared. And so I'm going to write down one more expression, and then I'm going to wipe off the board, bring the relevant things we've derived, and then restart. But the thing we're going to start with next time is that x, this unknown quantity here, is equal to the square root of r squared minus r minus h squared. So after I erase the board, we're going to simply just use some algebra to multiply this out, get some cancellations. And I'll actually just save you that and come back with just the simplified term. And then we're going to be able to put this all together with a few more just rearrangements and additions. We're going to have the density of the log floating in water, given that we know the radius. So we've come back. I've essentially just rewritten that the area of the log is equal to the submerged area plus the floating area. We have this little baseball diamond looking thing, or this area of the sector minus the area of the triangle is equal to the floating area. the area of the sector is equal to r squared times the arc cosine of r minus h over r. Density of the water times the area of the submerged section is equal to the density of the log times pi r squared, and then the x is equal to this, and where x is this area on the triangle. So, to move on a little bit, I have written here that the formula for the area of a triangle, 1/2 base times height, where our base is x. This is being substituted in, times the height, which is r minus h. We're actually not going to do any simplifications here. All we have to do is use these equations that we've written, and just introduce a few things, and we have this problem solved. So to start off, what we are looking for here is actually this area. We want the submerged area, because we have here that the submerged area times the density of water, 1,000 kilograms per cubic meter, is equal to the density of the log, what we're trying to find, times pi r squared. This can also be rewritten as the density gamma log is equal to density of water, submerged area, over pi r squared. It's a pretty simple equation. So, the AS here is actually just equal to the submerged area. So, the first thing we need to find is the floating area. So we have all the equations to find that. We just take 1/2 2HR minus h squared times r minus h. Times the square root, sorry. Subtract that. I actually don't need these parentheses. You can subtract that, or you subtract the total area of the sector, which is r squared arc cos of r minus h over r minus this in brackets, and then you just so we have that, and as we see here, that'll give us the area of that'll actually just give us the whole area, so of the floating area. And so now we just take pi r squared minus that, and that gives us the submerged area. And then we have AS. This is all over pi r squared. And just multiply that by the density of water, 1,000 kilograms per cubic meter. And that equals gamma L, density of the log. So we have 1,000 times pi r squared, which is the cross-sectional area, minus r squared, the radius, times the arc cosine of r minus h over r, minus 1/2 of the square root of hr, or 2hr, lost in translation, 2hr minus h squared times r minus h. Probably best put this in parentheses. So, that is our solution. Thank you.